Hello students, in this lecture we will see the next carrier transport phenomenon, that is the Hall effect. So in order to understand the Hall effect, consider the p-type semiconductor bar. So let's consider this is the p-type semiconducting bar and with thickness equal to T, and T will be the thickness of this bar and W will be the width of this bar. Let's consider the points. This is point A, this is point B, this is point C, and this is point D. And this will be the direction of current I, X, and positive potential is developed at this plate and negative potential is developed at this plate, due to which there is formation of electric field in this direction, that is in positive Y direction. So it is epsilon Y, and magnetic field is in Z direction. So this is the direction of magnetic field. So as the bar is p-type bar, and if a magnetic field is applied perpendicular in which the hole drift in p-type material, that is hole will flow from this point C to point D, and magnetic field is applied perpendicular to the direction of motion of holes in the p-type bar. So the path of holes tend to be deflected due to this application of magnetic field, and the total force, that is Lorentz force, which is acting on holes due to electric and magnetic field, is given by F is equal to Q into epsilon plus V cross B. So this is equation number 1. If we consider the force in y direction, then one may write here F y is equal to Q into epsilon y minus Vx bz. So this is equation number 2. The important result of this equation number 2 is that unless an electric field epsilon y is established along the width of bar, as this is the width of bar, and unless this electric field epsilon y is developed along this width of bar, each hole will experience a net force, and therefore it experiences the acceleration in negative y direction, and due to which these holes coming from this point C to point D will be deflected towards this plate at point A, and towards this plate the holes will be deflected, due to which positive potential will be developed at this plate and negative potential will be developed at this plate. So therefore, to maintain a steady state flow of the holes down to the length of bar, that is from this side to this side, the electric field epsilon y must be just balanced by this product Vx into Bz. So here, in order to make the steady state flow of holes from this point C towards point D, one has to balance this product Vx into Bz with this developed electric field. So one may write Ey is equal to Vx into Bz. So this is equation number 3. And due to which the net force, that is this force Fy, will be 0 due to this balancing of this product Vx into Bz with the electric field. Physically, the electric field shifts the whole distribution slightly in negative y direction, and once the electric field Ey becomes as large as this product Vx into Bz, no net lateral force is experienced by the holes as they drift along the bar. And the establishment of the electric field epsilon y is known as Hall effect. This development of electric field epsilon y along this direction, that is positive y direction, is known as Hall effect. So by using the current density equation, one may write Jx, current density along x direction is given by Jx is equal to Q into P naught into Vx. This is next equation number 4. So from this, as we have epsilon y is equal to Vx into Bz. So I may write here epsilon y is equal to Vx into Bz, and by putting the value of Vx from this equation number 4, we may write here Ey is equal to Jx Bz upon Q into P naught. So this is epsilon y, we got epsilon y is equal to Jx into Bz upon Q into P naught, and one may write it as RH into Jx into Bz. So this is RH is the Hall coefficient, and it has the value RH is equal to 1 upon Q into P naught. So this is next equation number 5. Thus, the Hall field is proportional to the product of current density and the magnetic flux density. This epsilon y is nothing but the Hall field, and which is proportional to current density and magnetic flux density. The proportionality constant RH is nothing but it is RH is equal to Q into P naught inverse. So, and this proportionality constant is called Hall coefficient. And from known values of current and magnetic field, we may write for hole concentration P naught is equal to 1 upon Q into RH, and by putting the value of RH from this equation, that is epsilon y is equal to RH into Jx into Bz, we may write here it is equal to Jx into Bz upon Q into epsilon y. By putting the value of RH or 1 upon RH from this equation, epsilon y is equal to RH into Jx upon Bz. So we got 1 upon RH is equal to Jx into Bz upon epsilon y, and we have put this value in this equation. So as Jx is the current density, so we may write P naught is equal to, in place of Jx I will write Ix upon W into T into Bz divided by Q into, in place of this electric field I will write here Vx, or sorry, this Ey is the electric field between these two plates. So I will write here VAB, that is voltage between these 2 points A and B upon W. So here WW, that is width of the bar, get cancelled, and we get P naught is equal to Ix Bz upon Q into T into VAB. So this is next equation number 6. So one may say that with the study of Hall effect, one may calculate the hole concentration or carrier concentration. Since all the quantities in this equation number 6, that is all the quantities at the right hand side in this equation can be measured, the Hall effect can be used to give the accurate values of carrier concentration. If one measures the resistance, the sample resistivity can be calculated, and which is given by rho is equal to R into W into T upon L, and which is equal to VCD upon Ix divided by L upon W into T. So this is next equation number 7. Since the conductivity sigma is given by sigma is equal to 1 upon rho. Sigma is equal to 1 upon rho, and which is equal to Q into mu P into P naught. So the mobility is simply the ratio of Hall coefficient and the resistivity over the range of temperature, which yields the plot of majority carrier concentration and mobility versus temperature. Such measurements are useful in analyzing the semiconductor material, and similar results can be obtained for the N-type material. A negative value of charge Q is used for the electrons, and Hall voltage and Hall coefficient are negative in case of when the semiconductor material is of N type. The Hall voltage is a common technique to determine for the unknown sample, that is the sample, that is semiconducting sample, is either positive or negative. In case when the semiconducting material is of P type, then Hall voltage will be positive, and in case when the semiconducting material is N type, the Hall voltage will be negative. So with this I will conclude this lecture. Thank you.